Hello and welcome to Engineering Ethics at NJIT. I'm your instructor, Daniel Estrada, and this is the Artificial Intelligence Lecture Part 2, where we will talk about the day that computers took over the world. What do I mean by the day that computers took over the world? Well, I mean May 11th, 1997, the Deep Blue versus Kasparov match where Deep Blue beats Kasparov. Kasparov's the world chess champion at the time. He had been the dominant chess player on the planet for several years before this. And Deep Blue was the supercomputer built by IBM, specifically designed to play chess to beat Garry Kasparov at chess. Kasparov had played Deep Blue before. In 1996, there was an exhibition match where Kasparov pretty easily beat Deep Blue. And before that, IBM had built other computers. One of them was named Deep Thought, that Kasparov had also played, and Kasparov had beat all those very, very easily. So when Deep Blue plays Kasparov and wins, this is a historic moment. This is the day that this is what I call the day that computers took over the world. Now, if you watched my history video in part 1, you know that I don't put a lot of stock into this rhetoric of computers taking over the world. This is used a little bit tongue-in-cheek here. But I use it for two reasons. One, first of all, it's a day in the past. So the day the computers took over the world is not some coming day in the future that we have to be worried about. No, in fact, the day the computers took over the world, I want to say, is in the past, and actually in the somewhat distant past, 23 years ago, where we already live in the world and have for some time. We've already lived in the world after computers have taken over the world. So thinking about this in the past, I think maybe changes our way of thinking about computers and what computers are doing. The other reason I like using this day as the day that computers took over the world is because for the longest time, chess has been a symbol of human rationality, a symbol of the kind of strategic, clever thinking that only human beings are capable of. I remember when this chess match happened, I was in high school at the time, and I remember reading articles before the event happened. A lot of them were skeptical that the computers were smart enough to beat chess champions. They would say things like, the human brain is too powerful, we're too good at pattern matching, we're too clever and quick, that no computer is going to be able to stand up to the human chess grandmaster. I mean, the computers can play good chess. If you're not very good at chess and you play one of these computers, it might beat you. But the top end of human performance, represented by Garry Kasparov, the world chess champion, is just too far beyond what even our best computers can do. I remember reading these articles, and then I remember watching the event, and Deep Blue beat Kasparov. In fact, beat Kasparov pretty handily in the second round. And then there were a lot of papers trying to walk back this claim and really trying to reflect about what it means that computers are now beating our top chess champions. So a little bit of a humiliation on the part of the humans. So I like rubbing it in humans' face that they got beaten by the computer. So I want to talk about this chess match. I want to talk about what happened. I want to talk a little bit about computer chess. But before we do that, I really want to start by talking about what it is to be a computer, so that we know in some detail what it is that has taken over the world. Now, in the history video last time, I talked a little bit about Alan Turing and his Turing machine. Turing was a mathematician, and in the 1930s, Turing proves an important mathematical result. He proves that the halting problem is undecidable. And the important thing for our purposes is that Turing proves this using his what he calls what has come to be called the Turing machine. He just calls it the machine. It's very important for Turing that this is the kind of machine that you can actually build in a machine shop. It uses the kind of parts. So this is not some far-off science fiction fantasy, some future technology that we don't know how to do. Turing is very clear that this is the kind of machine that we could build right now. And in fact, Turing does go on to build some of the first computers and using his original design. Now, his design is pretty abstract. He doesn't really tell you what the mechanisms involved in the Turing machine are. He just tells you how the different parts are related in order to perform computations. Remember from the history that before Turing's machine, we really didn't have a notion of mechanical computation or automated computation. and that a computer was the person that you hire to do computational work, to do calculations, usually mathematical calculations. And so before Turing was around, there really wasn't a good definition of what a computer was or what a computation was. Even mathematicians didn't have a solid sense of what it meant to compute, and this is partly what Turing's machine is meant to solve. With Turing's machine, Turing can give a formal definition of computation, and he uses this to prove that the halting problem is undecidable. So let me tell you a little bit about the halting problem. So in computer science speak, a given program will run through some processes, but then it will eventually halt. So the halt state is the final state of the machine. It's the state that the machine reaches when it goes through all its computations and gets its end result. So an interesting question is, when will a machine halt? Like, you're running a program, you don't know how long the program is going to take. When will the machine halt? If the program is simple enough, and I'll show you a simple enough program that we can actually run through it, then you can just go through the steps and see that the machine will halt in 20 steps or 30 steps or whatever. If the algorithm is simple enough, the program is simple enough, then you can tell by hand, just calculate out when it's going to halt. What Turing is worried about is there any general procedure for any given program? Can you tell how many steps it'll take to halt? Is there a general algorithm for determining when a given program will halt? At the start of the 20th century, a lot of mathematicians thought there was, and thought it was just a matter of time before we found these algorithms, and then we can start sort of automatically proving mathematical theorems and so on. So one of Hilbert's 20 questions, sorry, not 20 questions, it was like 23 questions, but he had these big mathematical questions for the 20th century, open questions. At the turn of the 20th century, he published this paper where he lists these open mathematical problems that have yet to be solved. Several of them have been solved yet, some of them haven't been solved yet, but one of them was, can you give a general method of proof for any given theorem, or in Turing's terms, can you tell when a given program will halt? So everyone thought that you would be able to find this general purpose algorithm for determining whether a program will halt. And what Turing shows is that, in fact, the halting problem is undecidable. It's not possible in general to determine whether a given program will halt. In some cases, the fastest way to tell whether a program will halt is just to run that program and see what happens later down the road. The problem is that some programs run on forever. They have an infinite loop and they go on forever. And other programs run for a very, very long time, but then eventually halt. And part of Turing's point is that you can't always tell the difference between these two. In some cases, you can't determine in advance whether a machine will halt or not. And part of the way he does this is by constructing what he calls a universal Turing machine. So a single Turing machine runs one program, performs a set of computations, and reaches a result. So an individual Turing machine, you might associate an individual Turing machine with a single program or single step set of operations. The universal Turing machine is a Turing machine that can perform whatever operations any other Turing machine can perform. This is the sense in which it's universal. It's universal because the universal Turing machine can do whatever any other Turing machine can do. And the way that Turing finds the universal Turing machine is by encoding the program in the regular Turing machine into binary code. Right, so once you have a method for encoding a program into ones and zeros, then you can put the program onto the memory, and you can give that memory to any other program. And so a universal Turing machine is a Turing machine that accepts as input the binary representation of any other program, and then that universal Turing machine can run that other program and then get whatever results that it would get. So the universal Turing machine, in this way, can do the work of any other Turing machine, because it can read that machine in as input and then execute its program. And what Turing proves is that not even the universal Turing machine can solve the halting problem. So if the universal Turing machine can do the work of any other machine, and the universal Turing machine cannot solve the halting problem, then no other machine can solve the halting problem. The halting problem is undecidable. This is a brief overview of how Turing gets to this result. What's important for our purposes is that Turing's machine gives us a formalization of computation, and it allows us to actually start building these machines to be effective. We can actually build working Turing machines. We'll talk a little bit more next time about the universality of digital computers. On my view, this is what really convinces Turing not only that computers are very powerful, but that also computers may eventually be able to think. If a universal Turing machine can do the work of any other machine, then the brain's a machine. Maybe if the universal Turing machine can do the work of any other machine and the brain is a machine, then the universal Turing machine can do the work of a brain, in which case the Turing machine has the same intelligence or can perform the same operations as a brain. And if one of the operations that brains can perform is thinking, then you can build a universal Turing machine that can think. Right, so reflections on the universality of these machines, the fact that they can do the work of any other machine, I think is really central to is the key move in thinking about thinking computers, or whether computers have minds, whether computers can think. If a computer can be a universal machine, then maybe computers can think. So this is supposed to be provocative. I want to get more into these philosophical arguments in part 3 of this lecture. What I want to do now is reflect a little bit more on how these programs work. So here is a program. Let me just blow up that program. So this is the program of a Turing machine. And again, remember, the mechanisms of the machine itself don't matter as much as the program, because the program is what's controlling everything. A typical way of writing these programs is in what's called a state table. So in Turing's machines, these are state machines. And so the idea is that there's some number of states. In this case, there's 3 states: state A, state B, state C. And A is the start state, and there's also a halt state that you get to, you maybe get to. So this is a 3-state machine, and there's also 2 different symbols. There's the 0 or a blank on the tape, and then there's a 1. And so what this table does is it tells you, given the state that you're in, if you're in state A, state B, state C, and you read the symbol from the tape, this is the instruction that you do. So if you're in state A and you read tape symbol 0, then the instruction is that you write symbol 1, you move the tape 1 to the right, and then you set the next state to B. So now we're in state B. Say we read in another 0, then we write a symbol 1, we move the tape 1 state to the left, 1 space to the left, and then we set the current state to A, and so on. So so each one of these entries here is an instruction, and different states have different instructions, and those instructions also depend on what symbol is being read on the tape. So the head is at some point in the tape, and what symbol is the head reading. So the table that you see here effectively describes the program. This is a particular program. This is actually the 3-state busy Beaver program. And this is a program. The program controls the computer. Again, you can write this program in 1s and 0s and store that program on the tape. This is what allows computers to work the way they do. But you can also represent these programs in lots of different ways. Here's a representation in the state table. Here's another way of representing the very same program. So this is the same 3-state busy Beaver program, but a very common way of representing these programs is with a state diagram. So in this case, instead of having columns for the different states, I'm symbolizing the different states as these circles. So A, B, and C are the different states. And then there's these transition between states, these arrows. The arrows transition between states depending on what they read. So the symbols here is before the slash is what the head is reading from the tape, and then after the slash is what's executed. So the P means print, in this case print a 1. All of the P's are print 1. If it's an E, it would be erase, and it's the same thing as printing 0. So P's are print 1s, and then L or R is moving left or right. And remember, this is what the head can do. It can read from the tape, it can write to the tape, and it can move left and right across the tape. So again, you start in state A, and if you're in state A and you read, let's say, a 1, if you read a 1 on state A, then what the diagram says is that you move to state C, you print a 1 on, if you read a 1 and you're in state A, you print 1, you move the tape 1 to the left, and you set your new state to C, which is the same thing it says here. If you're in state A and you read a 1, you write a 1, you move the state left, you move the tape left, and you set the next state to C. So this state diagram is just a translation of this state table. These are representing the same program. Again, and you can represent this program in binary code. It would be a little bit harder to see what's going on. The state diagrams are useful once you get used to them because they show they give a sort of top-down view of what's going on with the program. So you can see that from A we can go to B and C, and B goes to A or back to itself. But C is the only one that actually gets to the halt state. So this double circled state in the corner, this is the halt state. That's the goal state. What we want to do is get to this goal. And you can see that the only path to this goal is from state C if you read a 1. So the only way we're ever going to halt is if we're in state C and we read a 1. And that moves us to the halt state. If we're in state C and we read a 0, we move back to B. If we're in B, a 1 stays in B, a 0 moves to A. If we're in a 0 goes to B, and a 1 goes to C. So we can see that here, in order to get to the halt state, we actually need to go from A to C, and then from C to the halt state, because A is the only thing that goes to C also. So we can jump. So the idea is that we can jump back and forth between A and B, and we can jump around B a bunch of times, jump back and forth between A and B. But eventually we have to get to C and then get to the halt state, and that's how we finish the program. So this is a Busy Beaver program. If you've done computer science, you might know about the Busy Beaver programs. These are programs that are designed, they're designed to be as busy as possible. In particular, the goal of a Busy Beaver program is to write 1 as many times as possible on the tape, and to do it using the shortest program as possible. So the game of Busy Beaver programs is to try to make as short a program as possible that writes as many 1s on the tape as possible. So this is a 3-state, 2-symbol Busy Beaver. It's a very small program, and I think it writes like 20-something symbols. We can actually go through. So I actually want to work through this example in some detail. If this is boring to you, you can skip forward. I'm not going to be doing this very long. But I want to move through. So we're on. This is still the Busy Beaver program. But what we're going to do is we're going to actually look at the state of the tape as we go through different steps, and you'll see that this actually reaches the halt state after 14 steps. In halting after 14 steps, and it actually writes 1, 2, 3, 4, 5, 6. It writes 6 1s on the tape. So this 3-state, 2-symbol Busy Beaver program has a score of 6 because it ends up writing 6 when it hits the halt state. This is not the best 3-state, 2-symbol Busy Beaver program. I think you can do better than this, but this is a very simple one to go through. So the instructions that we're getting are the program that we're following is just this state table. This is the state diagram for the same state table. We're starting in a completely blank tape, so all the symbols on the tape are 0, and then the head of the tape is right here in the middle. All these underlined ones are where the head is. And also we start in state A. Okay, so we start in state A. Here's the head. We're looking at a 0. And the program tells us that if we're in state A and we read a 0, what the program says is first write a 1. So we're going to write a 1 here. And then it says move the tape 1 step to the right. So we're going to move the tape that way. And then we set our next state to B. And we can see that this is what in sequence step 2 here. Once we've executed all those things, now we're in step 2. And you can see that it's exactly as we would expect. So starting here, we write 1, we move the tape 1 over, and then we set state to B. So in step 2, we're in state B. The head is on this square, and 1 square to the right is now a 1. This is the one that we just wrote. So now that's here. And we're in state B. So if we're in state B and we read a 0, state B, reading a 0, it says write 1. So write 1 here, and then move the tape to the left. So move in the other direction. And then the next state is A. So we write a 1, we move to the left, and so now our head is on this square. So now we're on top of a 1. We have 1 written to our left, and our next state is A, just like we expect following this instruction. So this is what a computer is doing. It's just following these very simple instructions, these very simple operations that involve reading to, writing from memory, and then moving memory around so you can access different parts of memory. And that's all you need to perform computations, and Turing shows that this is enough to be a universal computer. These kinds of operations are all you need to do universal computation. Now, it's only 14 steps, and we'll see this start going pretty quickly, but we're on step 3 now. We have 1, 1. Our head is over this 1. Our state is A. So if we're in state A and we read a 1, the instruction says write 1, move to the left, and we're in state C. So from here, we write 1, there's already a 1 there, but we write a 1 again. Then we move this set one state to the we move the tape one square to the left. So these two 1s move over 1. And so now we're on this 0. And it says the next state is C. Oh, now we're in state C. Remember, state C is our ticket to the halt state. But we're not going to get it there. We only get to the halt state in state C if we read a 1, and right now we're reading a 0. So if we're in state C and we read a 0, it says write a 1, move the tape over to the left, and set your state to B. So our next state is B. We wrote the 1, and we moved the tape over to the left. So now there's 3 1s on to the left of the head. But we're still reading 0. Remember, the whole tape is full of zeros, so we're still reading. We're sort of moving zeros over from the right. So now we have this 0 at the head. And the program tells us if we're in state B and we read a 0, it says write a 1, move the state to the left. Write a 1, move the tape to the left, and set the new state to A. So write a 1, move the tape to the left. So now there's 4 1s to our left. We're currently over a 0, and we're in state A. State A says if you're in state A and you read a 0, write 1, move the tape right, and now you're in state B. So here we write 1. We write 1. We move the states to the right this time. So we have been moving to the left, but now we move to the right. And so now we're sort of in the middle of a bunch of 1s. We're at a 1 in the middle of a bunch of 1s, and so far we've written 5 1s. If we're in state B and we read a 1, it says move the tape to the right, and it says write a 1. It's already a 1, so we're just writing over this 1. We're writing a 1. It says move the tape to the left. So we move the tape to the left again. So now we have 2 on our left and 2 on our right. And the next state is B. So we're still in state B. If we're still in state B, we read a 1. Again, we write a 1. We move the tape over to the right, and then we set the state to B again. And so we're here with now 3 to our right and 1 to our left. We're still in state B. We're still reading a 1. So we write a 1. We move the tape to the right again. So now we're here. We now have 4 to our left and 4 to our right and 0 to our left. So basically, this long string of B's has just moved everything over. We really haven't written one. We haven't written a new 1 since we started this string of B's. We still have 5 1s on the tape. But now we're finally at a place where we're reading a 0. So once we move this over again, we're reading a 0. We're still in state B. So if we read a 0 in state B, we move the tape to the left. We set state to A. So now we're in state A. We moved 1 over to the left. So now we have 1 to our left. We still have 4 to our right, and we're on top of a 1. And now we're in the money zone, right? So if we're in state A and we read a 1, this is where we get into state C. It says move 1 to the left. So we move 1 to the left. Now we have 2 on our left and 3 on our right. We move 1 to the left, and then it says next state is state C. So now we're in state C, and we're reading a 1, and that's our halt condition. So if we're in state C and we read a 1, it says move the tape 1 to the right and halt. And so now we reach the halt state after 14 steps. And that's it. So we just went through the process that this computer would go, this 3-state Busy Beaver program would go through. We probably made it a lot more elaborate. I repeated myself quite a lot, but the computer doing this is also going to be repeating itself. It's going to be executing the same operations over and over and over again. And what changes is not the particular operation, but what's really changing is the state that the machine is in, because depending on the state, it performs different operations. If it's in the B state, it does this, and if it's in the A state, it does something different. And so by bouncing between these states and performing these sets of operations, you end up getting this Busy Beaver program that halts after it writes down 6 1s. Now, that's not a very useful program. Writing down 6 1s is not the most useful thing in the world. And you can imagine other very simple programs that write down 6 1s. What's sort of interesting about the Busy Beaver program is that it doesn't take a very simple program to write an incredibly huge number of 1s. If you go to the Busy Beaver Wikipedia page, it's linked up here, you can see that once we get into more states and more symbols, you have just huge programs that go on for a very, very long time. But this is supposed to, I encourage you, if you didn't follow that, I encourage you to try to follow along, see if you can actually go through the operations, especially if you've never studied computer science and you haven't done this before. I encourage you, because it's not very hard. In this framework, it almost doesn't even look like math. It's really just doing a set of regular operations of moving the tape back and forth and writing down 1s or not. And this is what the basic Turing machine can do. It can read from memory, write to memory, and move memory around so it can access different parts of memory. And those operations are enough to do an incredible variety of things. In fact, that's enough to be a universal computer, to do the work of any other computer. If you like Turing machines, or you just want more practice doing this, I also have, that's not what I want. I want this. I also have linked at the top of that slide to this Google Doodle. Google, sometimes changes its search menu to celebrate holidays or to respect artists or scientists or whatever. And so for Turing's 100th birthday, Google did this Turing Doodle, which is another Turing machine. You can see it's ones and zeros on a tape moving back and forth. And the game here is to write little programs in these nodes that turn this series of zeros and ones into this series of zeros and ones. So you can see that in this case, this second zero should be a 1, and that's the only thing that really needs to change. And this are just operations moving the tape back and forth and writing a 1 or a 0. It gets more complicated if you do a couple of these, but this is a fun little tool to sort of practice Turing machines and get used to the idea, or get into the mind space of these machines. Let's come back here. Okay. So this is a Turing machine. Hopefully that demonstration was a little bit helpful, just working through an example of a computer and sort of getting your mind into the headspace of a computer, what computers are doing. They're performing series of orderly operations. Another nice thing about this is that it gives you a sense of what a program is in a concrete way. Programs tell the machines to do specific operations in a specific order. And usually it involves these abstractions, these sort of state abstractions. Most computer programming today is not at this very simple level of binary code and very simple operations. Most high-level programming languages today can describe very, very high-level operations, very abstract operations, maybe transformations of data sets, like sorting the data set, for instance. And these kinds of high-level operations are executed by converting them into a sequence of low-level operations, just like this. In fact, all computers, any computer program that you've ever run can be coded into a series of binary operations, just like you see here. So this is what computers are doing at a sort of very technical level, sort of deep down. But I very strongly want to get out of the idea that all computers are things like laptops and desktops and your cell phone. I really want to get out of the idea that computers or programming requires something like binary code or digital circuits, electronics. None of these things are necessary for thinking about programs or thinking about computers. So I want to give just some other examples, and I'll do more of this in the next lesson when we talk about some of the philosophical dimensions of artificial intelligence. But before we get there, I just want to give a very simple example of another finite state machine, right? Another program. This time not describing binary operations in a Turing machine, but this time describing relatively high-level operations in a turnstile. So here's a turnstile like you would encounter at a bus station or a subway. You swipe your card or you put in some coins, and it unlocks, and you can push through. Usually these are sort of gated, so you can't walk around the turnstile. You have to sort of go through the gate. And these little bars prevent you from going through until you put in the coin or you swipe your card or you do something to unlock it. So this is a machine, and the machine goes through a couple of important states, and there's a couple of important operations that you can perform to the machine. And I've this is not my diagram, this is from Wikipedia, but here's a simple diagram describing the operations of this turnstile. So there's two relevant states for the turnstile. There's the lock state and the unlock state. Here's the lock state, here's the unlock state. The system starts in the lock state, and people who want to use it, they want to move the machine from the locked to the unlocked state, and in order to do that, you have to put in a coin. So for this machine, there are two operations you can perform for moving between these states. There's a push operation where you actually push through the turnstile. Then there's the coin operation, which is when you submit a coin or you swipe your card or whatever in order to move it from locked to unlocked. So here's the full state machine. Here's the full program describing the operation of this turnstile. So when it's locked and you try to push through, it's going to stay locked because you haven't put in a coin. So if you try to push through and it's locked, it just goes back to the lock state. But if it's locked and you put in a coin, that's what moves it to the unlocked state. If it's unlocked and you put in a coin, well, it's already unlocked, so that's not going to change anything, so it stays in the unlocked state. But if it's unlocked and you try to push through, well, it'll let you push through now, but it will also move it back to the locked state. So turnstiles bounce back and forth between the locked and the unlocked states depending on whether people put in a coin or push through. And this describes all of the possible operations and all of the states that the machine can get into and how those operations transition the machine from one state to the other. Notice that this is not a program described in binary code. This program can be realized by all sorts of different kinds of actual programs, by all sorts of different computer chips. You can have mechanical operations that are not digital, running the same kind of program, performing these same operations and moving from state to state in this way. Notice that this state description, it's a program, but it's a very abstract program. It's not talking about the specific mechanisms that are being used. There's all sorts of other details about the turnstile that it leaves out. So notice in this image, the turnstile has 3 prongs, but the diagram here doesn't say that it has 3 prongs. This same diagram would describe a turnstile with 5 prongs or 7 prongs, or it would describe those turnstiles that work as a gate. They're sort of like a cage as opposed to just little prongs. You could imagine controlling all of those different turnstiles with this same basic program. In other words, this program is operating at a very high level of abstraction. In other words, we're choosing to represent the locked state and the unlocked state as just basic states. We can be more specific. We can try to look at the specific mechanisms that is using to lock or unlock and talk more specifically about those. Maybe there's some program, this one looks like a card swipe one, so maybe there's some elaborate program that has a bunch of other states that it uses in order to test different things to make sure the card is a valid card and so on. So that might involve a more elaborate state diagram. But this diagram, at a certain level of abstraction, is perfectly adequate for describing this turnstile. It doesn't require. None of this requires that the turnstile is electronic. It could be a mechanical mechanism. It doesn't require that it's run by computer chips. It's just describing the abstract state structure of the machine. So in the next lecture, I'm going to give you a couple more examples of state machines describing dynamical systems, and I'm going to try to argue that we can describe human beings, and especially we can describe infant babies in terms of state diagrams like this. But that's in lecture 3. What's important for our purposes is that the state machine framework that we've been using to talk about these Turing machines describes a certain kind of complexity, and it's the complexity of the automata. So a Turing machine is a kind of automata. It's a system that performs a set of operations. And what computer scientists have done in various ways is describe automata theory, which is to describe, given the kind of system that you are, given the kind of operations that you can perform, what can you do? So this is the full classification of the automata, the different kinds of operations you can perform and what you can do. And what you see here is that the automata hierarchy is actually very shallow. There's not that many different kinds of automata. And that's really because at a certain point, Turing machines are universal, and so there's not a big difference between different Turing machines. So anything that's a Turing machine is equivalent to any other Turing machine. This is the universal Turing machine makes it clear that any universal Turing machine can do the work of any other Turing machine, and so in some sense, all Turing machines have the same capacity. But Turing machines are also an idealization. Remember that the memory in the Turing machine goes on forever; it's infinite. And we can't actually build an infinite machine. So any real-world machine has finite memory. And the extent of what things with finite memory can do, in automata theory, those are called push-down automata. So push-down automata can do any set of operations that a Turing machine with finite memory can do. If the Turing machine has infinite memory, then it's a full-fledged Turing machine. But we can't actually build those. So any real-world computer, like the computer in your desk, your cell phone, your laptop, those are all push-down automata. Push-down automata have memory. You don't always have to have memory. In fact, this simple turnstile diagram that we went through, it doesn't have memory. It just moves from the locked to the unlocked state. One way you can tell that is if you keep putting in coins when you're in the unlocked state, it doesn't change what's going on in the program. So you can keep feeding in coins, and once you push through, it's not going to give you back those coins. If we were designing this in the real world, this isn't a very user-friendly design. We would probably want to do something like if the user gives more coins than are required. In other words, if we're in the unlock state already and they keep putting in coins, then maybe we return those coins as the user pushes through. And this system can't do that because it doesn't tell you, it doesn't remember how many coins are being put in. Every time you get a coin, you just go back to the same unlock state and nothing changes. So it sort of forgets immediately what happened in the past. It only remembers what state it's in. So in order to change this, what would be useful is to add memory, maybe have a counter, so that every time you go through this loop, you increment a counter by 1, and then when you push through, you return that counter minus 1 coins. Right? So if they put in 10 coins and it only requires 1 coin, then when you push through, you give them 9 coins back because they put in 9 coins too many. But in order to do even that kind of simple operation, you need memory. You need to remember how many times you're moving through these different pathways. And that's not something that a regular finite state machine has. So a push-down automata has memory. It has finite memory. A finite state machine only has its states. It only has the states and the transitions between the states. Turns out you can do a lot of really interesting things with finite state machines without any memory at all, but you can't do everything. There are some computing tasks that require some amount of memory. But as soon as you have any memory at all, you can do, there's algorithms for trading out memory with time. So if you have even just a little bit of memory, you can use that little bit of memory to perform the same operations that any other push-down automata with memory has, no matter how much memory they have. And in fact, the only difference between push-down automata and the Turing machine is that Turing machine has infinite memory, but you can swap that out with time. So you can also push-down automata with an infinite amount of time can do the same thing that a Turing machine with an infinite amount of space can do. Finite state machine can do a little bit less. The sort of simplest automata are, simplest automata are these, is just set theory and first order logic. Combinational logic allows you to perform certain kinds of computations, certain kinds of logical operations, but you can't do a whole lot, especially if you don't have states. So this is the hierarchy. The simplest things is just formal logic, symbolic logic. Then you have states, then you have memory, then you have infinite memory. That's the automata hierarchy. And again, most computers that you interact with are just push-down automata. But talking about the kind of agent that you are, the kind of automata that you are, isn't really useful because the stack is so shallow that most agents that you run into are push-down automata, because most agents have some memory. So it's not really terribly useful to classify things according to their place in the automata hierarchy. What's a lot better is looking at the problems that different automata solve and how long it takes to solve it. This is a typical thing that you might see in a computer science class. These are different sorting algorithms. Let me actually start from the beginning again. So you start off. So each of these start off with a set of random numbers, and the task is to sort these numbers from lowest to highest. And so you can see here, shell sort, quick sort already have the entire data set sorted, and these other processes are taking a lot longer time. So some of them are going to take very, very long. They're just not very efficient algorithms. I think the fastest one here was quicksort, followed by shell sort and merge sort pretty quickly, heap sort also. So some of these are pretty quick. The fastest possible time that you can sort is n log n. This is the big O notation in computer science. Is the complexity of the problem, which is really just how long it takes to solve. Shell sort and quick sort are n log n time complexity, which means it takes on the order of n here is the number of things that it's sorting, and it takes n times the log of n for quick sort or shell sort to solve. Selection sort and insertion sort and so on, bubble sort, these take a lot longer. Sometimes in the worst case they might take n squared or the square of the size of the input to solve it. And that gets into exponential time, and that's really bad. N log n is pretty good time. N time is linear time. Notice that these are times that it takes for different algorithms to solve this problem. And the fastest you could possibly solve it is n log n. So what we're interested here is not in the complexity of the agent solving it. What we're interested in really is in the complexity of the problem. I'll say that the algorithms that are doing all of these, they're all push-down automata. They're all using states in memory to solve these problems. So the same push-down automata can solve all these problems. It just takes different time. So different push-down automata will require different amounts of time to solve the same problem. So what computer scientists are they're not really worried about the different kinds of automata, and they're not really worried about how long it takes different theoretical computer science is not worried about how much it takes different. You might do a bad program, you might run a bad algorithm that takes a long time, but some algorithms run that same problem much more efficiently. And what computer scientists are generally interested in is the hierarchy of problems. So which problems are fundamentally harder than others? Which problems necessarily take more time than others? Right. So if some problem can be solved in n log n, that's pretty good. If a different problem requires n cubed time, then that's much worse than n log n. And if it's not possible to solve that problem faster than n cubed time, then you have this structure of problems where some problems are just harder than others. And this is what computer scientists are really interested in. This is the complexity hierarchy. The complexity hierarchy is not a hierarchy of agents. It's not what are the kinds of things that can solve these problems, because the kinds of things are all the same. They're all Turing machines, or they're all push-down automata. The interesting question for computer scientists is, what are the problems that you're solving? Because some problems legitimately are harder than others. At least we think so. So this is a representation of the space of problems and how the different spaces relate to each other. One of the famous spaces is P. These are the problems that can be solved in polynomial time. NP are the problems that can be these are the non-deterministic problems that can be solved in polynomial time. The N stands for non-deterministic polynomial time. So P are problems that can be solved in polynomial time and are deterministic. NP are the non-deterministic polynomial time problems. And we think that NP is a bigger complexity space, that NP problems are harder than P problems. In fact, a lot of people think this is the case. Most of what we've seen from the mathematics, from the computer science, suggests that NP is harder than P. But we actually don't know this. This is one of the old Hilbert's mathematical problems that's still unsolved. This is maybe the most important mathematical problem that's unsolved. It's certainly the most important computer science problem that's unsolved. Maybe the Riemann hypothesis is more important in mathematics. But there's $1 million prize to anyone who solves does P equal NP. If you can prove that NP problems are definitely harder than P problems, or if you can prove that NP problems have the same complexity as P problems, either way you get $1 million. There's a lot of people trying to solve this. We still don't know how to solve it. But what we do know is that if P does not equal NP, then the complexity space has a lot of very interesting structure. The relationship between standard von Neumann machines and quantum computers is also a very interesting problem in terms of complexity hierarchy. It seems like there are certain problems that quantum computers are better at solving than regular computers, or classical computers. And so understanding the structure of problem space, this is where all the good computer science issues are. And this leads us back to our discussion of the day the computers took over the world. The reason that chess is so useful in studying intelligence, but also studying how intelligent computers are, is because chess is a very complicated problem. The search space for chess is extremely difficult to search. This is why it's so hard to play chess. Is the problem space is so big. There's so many different operations that you can perform in chess. There's so many moves that you can make that it's really hard to find which move is the best. So let's get back into this game. Actually, before we get back into this game, let me talk to you about the complexity of chess, the problem space of chess. If you know chess, this is a chessboard. If you don't know chess, you don't need to know too much about chess in order to follow what I'm going to say. But this is the starting state of the chessboard. These are pawns. They all move in the same way. A pawn on its first move can move 2 spaces, but on the other moves it can just move 1 space, and pawns attack by attacking the diagonal spaces. So white is moving its pawns this way, and black is moving its pawns this way. And then the back row has all sorts of different pieces, the rook, the knight, the bishop, the queen, and the king. The goal of chess, all these pieces move in different ways. The goal of chess is to attack the other person's king in a way that can't be in a way that they can't defend. If you can attack their king and they can't defend your attack, this is called checkmate, and then whoever does that wins the game. So how do we know how complicated the problem space of chess is, and how do we build a computer that can play chess? So I want you to think about chess the way that a computer scientist will think about chess, and this is going to build on this discussion of state diagrams that we did earlier. So imagine this is the starting state of chess. How many moves? So white goes first in chess. How many moves can white make on its first move? Think about it for a second. How many moves can white make in its first move? How many possible moves does white have to choose from? So remember I said that all of the pawns here can either move 1 or 2 spaces in the first move. So there are 8 pawns. So that's 16 possible moves with the pawns. But there's 2 other moves, 4 other moves that white can make. They can also move their knight. So this knight can move here. Knights move in L shapes. So it's up 3 and over 1. Or up 3 and over 1. So this knight can move here to this black space. They can also move here to this black space. And this knight can move to this white space or this white space. So all of these pawns here or here, that's 16. And then 17, 18, 19, 20 for the knights. So white has 20 possible moves in the first move. There's 20 options to choose from. And how many responses does black have? Well, black can do the same kinds of moves. Black and white cannot interact on the first chess move. So black can also move all its pawns up 1 space or 2 spaces. It can also move the horse here or here, and this horse here or here. So that's 20 possible moves. So white has 20 initial moves, and black has 20 responses to each one of those moves. So we can diagram this as a tree. So imagine here that this is the same chess game. Imagine that the initial state of chess, this opening board position, imagine we represent that as this root node of this tree, and then we have 20 possible moves that white can make. So each of these connections to the red squares here are all of the different moves that white can make. So this is like moving 1 pawn, and this is moving a different pawn, and this is moving that pawn twice, and so on. So all 20 of the moves that white can make are these red squares. And then for each red square, black has 20 possible responses. So the diagram here only shows 20 responses to this one red square, but imagine that each one of these red squares has 20 black responses off of those red squares. So 20 possible white moves, and then for each one of those 20 possible black moves, that means that there's 400 possible moves in just the first set of moves in chess. So white moves first, and then black moves, and that gives 400 possible moves for just the first move in chess. Now, the average number of games in chess is 35 moves or so. So imagine drawing out this whole tree, 35 moves down, so that at every move you lay out all the possible moves. For each move, all 35 levels down. You're going to have a huge tree. This is giving you a hint of the size of the chess search space. If you fill out all of these possibilities for 35 possible moves, you have the size of all of the possibilities that are being considered in an average game of chess. But that's just the average number of moves. 35 moves is the average number of moves. A chess game can go on much longer than that. It can go on for hundreds and hundreds of moves, depending on the circumstances. The end game scenarios can go on for long periods of time. So imagine trying to fill out this full chess tree for all possible moves, all possible games, to give a complete representation of every possible move in chess, every response for all possible games. In other words, filling out this chess tree completely. So it would be a huge tree. To give you some sense of how big this would be, Claude Shannon, back in the 50s or 60s, calculated, did some back of the envelope kind of calculations to figure out how big the chess game space is, how many possible games of chess there are. Possible games of chess would be one route down this tree, right? So different games of chess are different routes down this tree. And Claude Shannon wanted to know how many different possible games of chess are there, how many different games of chess can you play, selecting one move from each of these rows. And doing some back-of-the-envelope calculations, Shannon calculates that there's 10 to the 20 possible games. 10 to the 120 possible games of chess. So 10 to the exponent of 120. That's huge. That's an extremely large number. To give you a sense of how large that is, there are about 10 to the 80 particles in the universe. That are in the observable universe. That's 10 to the 80 like protons, like individual protons. So 10 to the 80 particles, 10 to the 80 protons in the universe. There are 10 to the 120 possible games of chess. There are more possible games of chess than there are protons in the universe. What that means is that if you were to write out one game of chess on every proton, you would run out of protons before you ran out of games of chess. And what that means is that you really can't write out all the games of chess in this universe. There's not enough protons in the universe to write down all the games of chess. Even if you were encoding one game per proton, you would run out of protons. So the game of chess is just too big. It's too big to represent in this universe. It's too big to actually search that entire space in our lifetimes. Chess is astronomically big. It's not possible to solve it. Like logically, it's possible to solve it. Like you can imagine going through the process of filling out this entire tree. It's just that you would run out of time. Like it would go on forever because it would take so much time, and then you'd run out of space in the universe to actually write the whole tree down. So we're never going to actually solve chess in this way. We're never going to actually build this complete tree. There are some games where we have solved the entire thing. These are called the solved games, where we've built out the tree that represents every possible move you can play. So, for instance, we've done this with Connect 4. Connect 4, the little chips in the slots, and you have to get 4 in a row. It's a little tabletop children's game. We went through and played every possible game of Connect 4. So if you went and played in every possible row, we had computers go through and play every possible game of Connect 4. So we filled out the whole Connect 4 tree, and so it's a solved game. And because we've solved it, we know that it's not a fair game. Connect 4 is not fair. The player who starts the round can force a win. They can make it so that they always win. Connect 4 is not a fair game. If you ever find yourself playing Connect 4 with your family, you might want to mention that it's just not a fair game. It's not very fun to play. It's not trivial to find the best response. Sometimes it can be a little bit difficult. But Connect 4 is a solved game. Checkers is also a solved game. Sometimes checkers is thought about as the sort of easy version of chess. In checkers, the board is the same, and the setup is a lot easier because all of the pieces are exactly the same when you jump over other pieces. I'm sure a lot of you have played checkers. Checkers is also a solved game. We've played through every game of checkers. When I say we, I mean computers. We set up computers to go through every possible move and play through every possible game of checkers. And we've done this. We've gone through every possible game of checkers. And because we've gone through every game, we know that checkers is a fair game, that red and black both have opportunities to win. They have the same chances of winning. So the person who starts in checkers doesn't have an advantage in checkers. I think checkers is the largest solved game we have to date. The search space is huge, 10 to the 20. But it's not anywhere near as big as chess. Chess search space is 10 to the 120. Another solved game you're probably familiar with is Tic-Tac-Toe. Tic-Tac-Toe is a solved game. In fact, this is from an XKCD comic where Randall actually works through every possible game. So if X's first move is in this corner, and then say O responds in this top space, then X can respond in the center, and then you can see that this plays out all possible games here. But if O responds in this corner, then this plays out those possible games, and so on. So this works out all the different possible games for X. This works out all the different possible games for O. This is not the complete map. You can see that X, it doesn't show the cases where X starts on one of the side spaces, but that's because those aren't very good moves. So the best move is always in one of the corners, and then this framing is rotationally symmetric. So if you rotate it around, you're going to get the same map for starting in any of the other corners. But this is the complete map for tic-tac-toe. The complete map, you can see there's a lot of possible games of tic-tac-toe, but it's really not that many. It's enough that you can go through and diagram the whole thing by hand. It's enough that you should be able to have in your head every possible game of tic-tac-toe such that you never lose. If you're older than 6 years old, you should never lose tic-tac-toe. Every game of tic-tac-toe between two competent adults should end in a draw. Tic-tac-toe is a small enough game that you're able to see what paths lead to success and what paths lead to failure, and that both players have enough tools at their disposal to make sure that it always ends in a draw. If you play a game of tic-tac-toe and it doesn't end in a draw, there's something went wrong. Someone did not play correctly. So there's a lot of possible games here, but it's small enough that a human being can master. It's not possible for a human being to master checkers, even though we can get a computer that can play the perfect game of checkers. We can have a computer that will, at the very least, draw a game, if not win a game, against a human being. It's really not a point in having tournaments against computers, because computers can play the perfect game. But that's not the case with chess. You can't get a computer to solve... the chess game is too big for computers to solve, so you can't get a computer to play the perfect game. I mean, you might think Kasparov versus Deep Blue, well, it's no fair because computers can just know what the correct answer is. But part of the point here is that chess is too big, that Deep Blue can't know the answer from the get-go. There's no big table. You can just look up what the strongest move is. Instead, you have to actually do the calculations. Both Kasparov and Deep Blue have to do the calculations. Kasparov uses all sorts of pattern matching heuristics. He also trains quite a lot. But Deep Blue does the... Deep Blue plays chess in a way that's slightly different than Kasparov. It's sort of a brute force method. What Deep Blue really does is construct this tree. It actually builds and plays through every possible move. So I think Deep Blue, the figure is that it was calculating something like 200 million moves a second. 200 million moves a second means that it's going through and considering 200 million possible steps in this tree. Now, even going 200 million moves a second is not going to make a dent in 10 to the 120 possible moves. So this search tree is way too big to search the entire thing, so Deep Blue has to make some choices. So instead of considering all 20 moves for this first move, this is every possible move of the pawn, and some of those moves aren't very good, like moving the pawns on the side. You can do it. I think there's even a name for that move in chess, but it's not a very good move. It's not a very common move. It's not the kind of move that you see. A especially bad move is moving your horse to the sides as your first move. It's a very bad move. You're almost never going to see it in professional play. So one of the tricks that Deep Blue uses in order to find the best chess move is by pruning this tree, is just by cutting out some things, just not considering them. So White has 20 possible moves for the first move, but maybe Deep Blue only considers these middle 6 moves as any good, because those are the ones that comes up most often, and then it'll just ignore the other 14. If Deep Blue just ignores those other 14, all of the possibilities underneath those moves are also ignored, so this cuts out a big chunk of the tree. And maybe in the black case, it only considers these 4 moves and cuts out all the rest of them. So by doing this kind of pruning of the tree, you whittle the whole search space down to a more manageable size, and that starts to bring it into the realm where you can beat it with a computer. This is literally what Deep Blue does. Deep Blue prunes this chess tree. There's all sorts of techniques for pruning the chess tree, for making good decisions about what chess moves to consider in depth and which ones to just ignore. That's not all it does. It also has a very strong opening book. Like the first 20 or so moves for Deep Blue are all planned out in advance. Like if blue does this, then red should do this, and if blue does this, then red should do this. So the Deep Blue's opening book is all planned out. But after it gets about 20 moves in, then it starts going into deep processing, and this is where it's actually doing an evaluation, where it's actually considering different moves and trying to weigh them to see which one's stronger, and then eventually Deep Blue has to make a decision. And again, because the chess search space is so large, Deep Blue can't know in advance whether it gave the right answer. It has to make a choice. It has to make a guess. And that means it could be wrong. This is part of what makes it an actual competition. The question is really, can Deep Blue process chess moves faster, more efficiently, with better results than Garry Kasparov? Now, maybe here is a good time to talk a little bit more about Kasparov. Kasparov is a Russian chess grandmaster. He had been at the top of world chess. He'd been a world chess champion for, I think, decades before this. He's from Russia. He played in all sorts of major tournaments, and he was just a force to be reckoned with. Some people consider Kasparov to be one of the, or if not the best chess player of all time. They would say things like, so they rank chess players. You're initially a novice, and then you're a master, and then an international master, and then grandmaster. Grandmaster is the highest ranking that you can get in official chess. And they used to say that there were the grandmasters, and then there was Kasparov in a league of his own. Kasparov was in a field of his own, where he was winning these world chess championships over and over again, to the point that it almost didn't seem fair. Kasparov would do these exhibition matches where he would play 3 grandmasters at the same time. So he'd set up 3 chessboards and have 3 grandmasters, top-ranked chess players. There's only maybe 1,500 or 2,000 grandmasters in the entire world. So these are like the cream of the crop, best chess players in the world. And Kasparov would take 3 chessboards and put 3 different grandmasters on the other side of those chessboards and play all 3 at the same time, doing one move on each board and then cycling through the boards, playing all 3 chess grandmasters at the same time and beat them all. Kasparov would do the same thing, and he would blindfold himself and still beat 3 grandmasters at the same time. His powers were uncanny. In the early days of the internet, the early 90s, there was a website you could go to. It was very early internet. You go to this website, and it was Kasparov versus the world. So for a couple of months, I think they did this a couple of times, but for a few weeks or a month or so, there was a Kasparov versus the world game where anyone could show up to this website and vote on what they thought the next move should be in a collective game against Kasparov, and then there was a democratic process to decide what the next move would be. And Kasparov kicked the world's ass. It wasn't even close. In that kind of democratic process, the move that ends up winning usually tends to be a safe move, a predictable move, and it was a move that Kasparov could anticipate well in advance. And Kasparov knew exactly what to do with those safe predictable moves. So Kasparov could literally beat everyone in the world together or individually. There was no one who could beat Kasparov. He was the shining representation of human chess. And again, chess is supposed to be this symbol of human intellectual achievement. It was the game of kings. It was supposed to highlight our strategic, rational thought. And then Kasparov is supposed to be the best example that humanity has to offer of performance at this game. So this is really like our best human effort at the quintessential human task here at Kasparov. And this is really why computer scientists wanted to beat Kasparov at these chess playing programs. I mean, all the way back to Turing. Turing built programs to try to play chess, thinking that it would show something about the intelligence of the machine. And IBM had built several computers up to this point. And Kasparov had always beat them pretty handily. Deep Thought was not very hard to beat. Deep Thought was processing like something like a million moves a second. The first iteration of Deep Blue was doing something like 100 million moves a second, and then this version was special purpose hardware designed to process chess moves at 200 million moves a second. It was doing it in this straightforward brute force method of pruning this very large search tree, and that just takes a lot. It just takes a lot of calculations, a lot of computations. So Kasparov goes against Deep Blue the first time in 1996. I think Deep Blue beats Kasparov once in this first round, but it's a tournament, so it's best of 7. And even though Deep Blue beats Kasparov once, Kasparov beats Deep Blue a bunch of other times. They draw a couple of times. It's clear that Deep Blue is a very strong computer, maybe the strongest computer ever built, and that it can perform at near a grandmaster level. So anyone who is not a grandmaster playing this computer chess is probably going to get beaten. But Kasparov says that in a press conference at the end of the first Deep Blue match, there's a press conference, and Kasparov, thanks the IBM people, says, very impressive machine you built, very impressive engineering feat. But this machine is still just not at the level where it can compete with the top end of human performance. Human intelligence is just too clever that you're not going to get a machine to perform at this level, probably within our lifetime, Kasparov says. Probably not within my lifetime will I see a computer beat the world chess champion. And then 1997 comes around. In the 1997 rematch, Kasparov enters the rematch similarly confident at the end. So it's, again, a best of 7. Kasparov plays Deep Blue the first round, and Kasparov beats Deep Blue pretty handily. Again, Deep Blue plays a good game, but Kasparov knows what to do. Kasparov had played enough of these computers before, and Kasparov knew the kinds of tricks that work against the sort of deep brute force processing that Deep Blue was using. So Kasparov beats Deep Blue at the first match, and at the end of this match, Kasparov also has a press conference where he says, again, very impressive performance, but we're probably not going to get a computer that can perform at the level of the top grandmasters within our lifetimes. And then Game 2 rolls around. In Game 2, Deep Blue makes a chess move that ends up sacrificing the queen. The queen is the best piece on the board. The queen can run around the chessboard doing all sorts of work. So it's the most important piece, and it's also the piece that's that you should be protecting, second to the king, of course. But the queen's a very important piece, and Deep Blue makes a move that will result in the queen being captured, pretty clearly result in the queen being captured. But Deep Blue makes this move anticipating that once its queen is captured, it'll still leave Deep Blue in a better board position to eventually win the game. This is exactly what Deep Blue does, makes this very risky sacrificing move, and Kasparov is stunned, is just shocked, jaw on the floor, is just completely surprised that Deep Blue would play this very risky queen sacrifice move. At the end of this match, where Kasparov loses, instead of congratulating his opponents and expressing his admiration at the fact that Deep Blue beat him at the game, instead Kasparov calls foul. He calls shenanigans. He says, "Look, there's no way that computer could have made that move. That move was way too clever. It was way too smart. You didn't need to be a genius. It wasn't just me that could see an alternative. Any other grandmaster could have seen that there was this option of this risky queen sacrifice play." But Kasparov said, but a computer could not make that move. No computer could go in there, and it's not the kind of move that a computer would ever make. So Kasparov at the end of the game said that IBM must have been cheating. Kasparov said that he demanded to see the logs. He said that someone must have gone back there and switched around something in Deep Blue to make it win, because he just couldn't believe that a computer would make that move. But he doesn't get to see the logs. IBM refuses to hand over the logs. Part of the rules is that IBM can tinker with Deep Blue between matches, but not during a match. So after the end of the first day, they went in there and they did some things, made some adjustments. Same with Kasparov. Kasparov was allowed to talk with his colleagues. He has coaches and so on that he's talking with in between matches. But you're not allowed to mess with the machine during the match. As far as we know, IBM did not mess with the machine during the match, but Kasparov, after the match, did not believe that. He demanded to see the logs, and he was just thrown off his game after that first match. They get 3 more ties. Kasparov is not able to get an edge over Deep Blue for the next 3 games, and then in Game 6, Deep Blue again beats Kasparov. So that 3.5 to 2.5. This is the tournament. Deep Blue wins the tournament. Deep Blue wins 2 of the games in this set. Only 2 of the games, but it's really that second game where Kasparov is decisively beaten. Kasparov accusing IBM of manipulating the chess machine behind the scenes. What he was doing in chess history is called a Mechanical Turk. He was accusing IBM of running a Mechanical Turk. Mechanical Turk is the machine that you see in front of you. This is a machine from the 1700s, before modern electronics. But this is a chess-playing machine. Someone would present it as a machine from Turkey that could play top-level chess. And the person would open it up and you look inside, and it's just a bunch of gears and levers and wires and so on. And it's just this machine playing chess. In fact, this is a lie. The machine actually was able to hide a person inside of it, and the person had a way of seeing what was on the chessboard, and so using this to decide what moves to play. So the reason the Mechanical Turk exists at all is because, as I said earlier, chess is the game of kings. Kings like to play chess. Kings like to play chess and think of themselves as strategic, war heroes, war strategists. Chess is supposed to be a sort of model of the battlefield, and so kings like to play chess, thinking of themselves as sort of warrior kings. So kings like to play chess, but kings tend to not like to lose at chess. And sometimes it can be dangerous to beat a king at chess because maybe they'll arrest you or cut off your head or something. In particular, Napoleon loved to play chess, but Napoleon also had a very bad temper. And if you beat Napoleon at chess, he would throw a temper tantrum. He would get mad. He would yell at you. People sometimes feared for their lives, retaliation for beating Napoleon at chess. And what that means is that people tended to not beat Napoleon at chess deliberately. Napoleon loved chess, but he wasn't very good. But he thought he was good because anyone who played him would just throw the game and lose. And they would lose just because they didn't want to get Napoleon mad at them. So Napoleon went around thinking that he was really great at chess when in fact he wasn't. And this made a lot of chess players kind of angry. Like this guy doesn't. He thinks he's a great chess player, but he's not. And he doesn't know how bad of a chess player he is. If there was only some way of beating him at chess without getting in trouble for beating him at chess, well, what if there was a chess playing computer, the Mechanical Turk, so if the computer beats you, well, it's not a person. You can't hold a person responsible. You can't get mad at a person. It's just the machine. The machine's really good at what it does. So Mechanical Turk was not a real artificial computer computer chess player. IBM was. IBM is now in a museum. As far as I know, there's no evidence that IBM cheated during this match. It really doesn't matter if IBM cheated during this match, though, because computers have gotten faster in the time since, and the algorithms have gotten a lot better, that nowadays there's just no question. Computers are performing hundreds of points over the top-level human chess players. There's really no point in having a human versus computer chess tournament anymore because the computers will just wipe the floor with any human. And it's not just supercomputers that can do this. Your laptop is now fast enough that it can beat the world chess champion at chess. So there are no human versus computer chess games anymore. Instead, people play... so there's still human versus human chess tournaments now. The chess grandmaster today, or the chess world champion today, Magnus Carlsen, is the chess champion today. Some people say that he was better than Kasparov even at his prime. I'm not sure, but I don't know chess enough to say anything about that. Kasparov's still alive. He's retired, and he is sort of politically active. He's one of the big critics of Putin in Russia, and he's able to do it because he's also so famous, and it's such a mark of Russian pride that he can sort of be politically controversial a little bit. On the slide deck, I have a couple of documentaries about the Kasparov versus Deep Blue chess match that are fun to watch, if this is the kind of thing you're interested in. But yeah, like I said, there's still human versus human tournaments. There's also computer versus computer tournaments. And did I put this in here somewhere? Yeah. I should have put this slide earlier. But one of the slides in the deck is Stockfish versus Leela. So Stockfish is, I believe, the top-ranked chess computer program, and Leela is one of the contenders. Leela is also based on neural networks, and Stockfish is sort of classical brute force programming, similar to the way that Deep Blue works. So these chess matches between computers are still ongoing. This video is from just a few weeks ago, where people are still trying to figure out what is the best chess-playing computer and what is the best technique for computer chess. The recent successes with neural networks have sort of blown this open. So there's still things happening in computer chess that are interesting. And this is it's a good example of humans versus computers as a benchmark of performance. There's sometimes in computer or in artificial intelligence called human supremacy. So humans used to have supremacy at chess, but when Kasparov lost to Deep Blue, then human supremacy at chess went away, and now computers are the dominant chess players on the planet. And that's the case for a couple of other games, too. We've had, in fact, a series of both high-profile advertising stunts where computers play humans at various games. Somewhat on the same model as the Deep Blue versus Kasparov. A few A few years ago, in 2011, IBM built Watson. Watson it was an expert system. Watson is not a neural network. It doesn't use modern machine learning techniques, but Watson is sort of an expert system based on the old expert systems models, and it's just a really good database lookup system. And in particular, it can look up answers to databases in a language, things like trivia, and it can look things up by asking it questions. So Watson, you can ask it a question, and it can look up the answer to that question, and it can do it really fast, and it can do it fast enough to play Jeopardy! So in 2011, Watson played our two best Jeopardy! Players. This is Ken Jennings, who won the most consecutive games at Jeopardy! And this is Brad, I forget Brad's last name, but he won the most money at Jeopardy! So these are two best human players at Jeopardy! And they played against Watson, and you can see by the scores on the screen that Watson really just dominated the Jeopardy! I have a link to the Nova documentary where they go over a little bit about how Watson works and what it took to beat Jeopardy! Jeopardy! It's an extremely impressive performance. Jeopardy! Questions are not... So you might think, okay, so chess is big, but it's still just a bunch of formal rules. It's kind of like math. And computers are obviously good at math, so that's not so hard. But Jeopardy's really not like math. Answering trivia questions requires not just logical knowledge, not just sort of formal logic, but it also requires having a big a background of trivia. It requires doing things like dealing with puns and wordplay, which is not trivial to do, which is very hard to make rule-like operations to do things like understand a pun. So the fact that Watson can play Jeopardy! Fast enough to compete with human players is very impressive. And there have been other machines that do similar things. I think there are computers that are playing against high school students in Quiz Bowl and that kind of stuff. So humans no longer have supremacy in Jeopardy! Computers are really good at Jeopardy! Now. I just want to clarify one more time that Watson is really an old-style statistical learning machine. It doesn't use neural networks. It's really just a very fast database lookup system, and it makes it more or less like an expert system of the sort that Deep Blue was back in the 90s. And this is actually controversy about Watson. So IBM spent a lot of money advertising Watson. The Jeopardy! Match was an example of this advertising PR budget. But also in magazines and so on, a lot of people are familiar with Watson. In fact, Watson is probably one of the AI that people are most likely to name. If you ask people to name a real AI, people will name Watson, and that's really because of the marketing that IBM has done in getting Watson's name out there. But that marketing hasn't been really backed up with any results apart from the Jeopardy! Win. IBM really wanted Watson to be working in healthcare, to be organizing healthcare records, to help match doctors to patients, to help diagnose certain kinds of diseases. And after the Jeopardy! Win, Watson got a bunch of contracts from the medical insurance industry, from hospitals, to try to apply Watson's technology to medical concerns. And as far as I know, last time I checked, Watson has not been doing very well at these. A lot of these contracts have not been renewed. A lot of the claims that IBM has been making about Watson, like that Watson can diagnose better than doctors, these claims aren't really true. This might be a little bit of false advertising. It might also be dangerous, the kinds of situations that they're putting Watson in, not only for the patients, but also for the patient's privacy. So there's been a lot of blowback against Watson's use in medical records, and there's not a lot of results in these areas to show for. So Watson's kind of a hype machine, and you'll notice that Watson's Jeopardy! Match was right before the second golden age, and to some extent IBM could sense that there was another AI boom around the corner, and Watson was IBM's attempt to get ahead of that boom, to put a product out into market that was already available once the boom hit, so that people had something to start investing in. And IBM certainly took advantage of that advertising, but doesn't have a lot to show for it afterwards. There are a couple of other important matches between humans and machines that are worth talking about, and maybe the most important after the Jeopardy! One is AlphaGo. So this happened almost 20 years to the day after Kasparov lost to Deep Blue. The world Go champion lost to AlphaGo. AlphaGo is a a system built by DeepMind, which is the AI research division for Google. So this is not IBM anymore, and IBM workers were a little bit frustrated that Google took their play the best human strategy with Go. If you're not familiar with Go, Go is it's a board game very similar to chess. It's old, just like chess is thousands of years old. Go might be older than chess. It comes from China. And it's different in some ways than chess. You can see a game being played here on the screen. It's different in some ways from chess. It's similar in others. Some of the differences you see here is that the game starts off with an empty board, and play happens by putting pieces on the board, either these white or black stones. Notice that all of these stones are exactly the same, so unlike chess, there's not different kinds of pieces. All the pieces are exactly the same, they do the same thing. And you don't really move the pieces once you put them on the board. You can take them off the board, but you can't move them around the board, so Go is just putting a piece on the board. Another thing is, notice that the pieces are being put on the cross-section. So on a Go board, there are 19 lines, and the lines intersect at these crosses, at these intersections, and the stones get put over the intersections. So you're not putting the stone inside a square, you're putting the stone at the intersection of the square. And the reason for that is because the way that the game works is partly by surrounding other pieces. So the goal of Go, the goal that both players are trying to achieve is to occupy. So you're not trying to attack a specific piece or to capture a specific piece. What you're trying to do is just take up as much space as possible on the board. So as the players are putting down pieces, they start occupying space, and whoever occupies the most space in the board, whoever has the most regions under their control, or the biggest area under their control, by the time the game ends, and the game ends when the board is full. Usually the game ends well before the board is full, when it's pretty clear to both players who's going to win the game, and then they just agree to end the game there and consider it decided. So Go games usually don't go to the very end when the board is completely full. But the goal is just to take up as much space as you can. And you can do that without capturing any pieces. But it is possible to capture pieces, and this is how a lot of the game mechanics work. So you capture a piece by completely surrounding it. And by completely surrounding it, I mean you have a stone at every one of the intersections. So here's a black piece. If the white pieces were at this intersection, at the north, south, east, and west, north, south, west, and east, at the four corners here of that stone, if white player can get their stones on all four of those places, not at the diagonals, but just at the other intersections, then white has surrounded that piece and can capture it. And black can avoid capturing by putting another black piece next to its piece. So if black puts another piece here, actually, if we go down here, you can see here has two white pieces right next to each other, one on top of the other. So black had started surrounding this white piece, but then white put another piece here. And so if black wants to capture these pieces, black has to capture both of them together, and that requires surrounding the whole set. So that would require a stone here, 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 and here. In other words, it would require 6 stones to just capture these two. And you can start doing the math at how many required to capture 3 stones or 4 stones. It keeps getting bigger as these pieces expand out. And so this is sort of how Go works. So to prevent black from capturing this first stone, white starts developing out this sort of string. And maybe black can follow it. And the idea is that if white ever doesn't put down a stone, then black can eventually surround it and maybe capture that whole string. Okay, so this is how Go works. It's a very old game. It's very fun. I strongly encourage that you learn how to play it and play it a little bit. And Go is much, much, much bigger than chess. The size of the Go search space is something like 10 to the 170, which is many, many times bigger than the search space of chess. And I remember back in the 90s when the Deep Blue versus Kasparov match was going on, reading in the newspapers afterwards, where people saying, well, it's really surprising that Deep Blue can beat Kasparov at chess, but we're probably never going to see a computer beat the top Go players because Go is so much more complicated. The search space is so much bigger. And just to give you an idea of why the search space is bigger, well, first of all, the board is bigger. So there's 19 by 19 spaces. 19 by 19 is almost 20 by 20. 20 by 20 is 400. So when in Go, black goes first. So black has just a little bit under 20 by 20 or 400 options where to go. And then white can go anywhere else on the board, and so has something like 400 options responses. So just for the first black move and white move, it's 400 times 400, which is 1,600? No, 16,000? There's a lot of possible moves of Go. The search space just blows up really, really quickly. Because chess is a smaller board, and because chess also has certain kinds of pieces, they can only do certain kinds of moves. The search space in chess is much, much more limited than Go. Yeah, and like I said, I remember reading people saying that, okay, Go maybe a computer can do, but I mean, chess maybe a computer can do, but Go is just too big. It's just not going to happen, not in our lifetimes. And it took 20 years to do it, but it was in my lifetime at least. Maybe some of the people who were alive in 1997 are not still alive in 2017. But for the rest of us, we got to see both ancient human strategic games fall to computers over the span of these 20 years. The one on the bottom is when Alphago, which is the Go playing system from Google. So this isn't when AlphaGo played the top-ranked Go player. This is actually a side exhibition match where AlphaGo played not just one player, but played 5 top-ranked players. So in Go, the ranking is not Grandmaster, but they have a Dan, and they have different levels of Dan. Dan is sort of like a black belt, and so you can be a 1 Dan or a 2 Dan or 3 Dan black belt. And in Go, you can also be a 1 or 2 or 3 level Dan in Go, and the highest level Dan is a 9 Dan. So level 9 Dan is the highest ranking of Go. There's the sort of cream of the crop. And for this demonstration, Google asked 5 9 Dan players, so these are 5 of the top-ranked Go players, to all collaborate together on a strategy to play 5 against 1, those 5 against AlphaGo. They had a couple of weeks to prepare, and they had been meeting regularly before the match, going through plans of what to do against AlphaGo. And you can see the result here. They got stomped. They got stomped pretty badly. Here they're all holding their hands in their head after a humiliating defeat. So AlphaGo beat all 5 of these 9 Dan players at once. Some people call it a 54 Dan match. And AlphaGo beat them all. And then AlphaGo also played the top-ranked player, a guy named Kijia. It was a 3-game match, and AlphaGo beat all 3 games. Played top-ranked player. And so nowadays we know that Go is just better than human player. In fact, these games have been very influential in changing the direction of Go. The way that people play, especially at the top levels, the way that people play nowadays has been strongly influenced by Go. People are making moves and using strategies that they wouldn't have before because AlphaGo has shown that some of these strategies are actually viable. So we talked a little bit about how Go works. The way that AlphaGo is able to tame this huge search space of Go is you can't do a brute force method. Brute force barely works for chess, and it's not going to work for Go. So instead, DeepMind came up with a technique for searching the space efficiently. And this is not just for searching Go spaces. This is not a technique that DeepMind came up with. This has been around for a while. It's called Monte Carlo tree search. If you're in a data processing scenario and you see the words Monte Carlo, it basically means random. And so the technique for AlphaGo is a Monte Carlo tree search, which is a random tree search. So basically, you can't construct the entire chess tree from the beginning all the way through to every possible move. So what they do instead is they randomly select regions of the tree to search from, and they do this kind of Monte Carlo statistical search where they sort of take they sort of sample different places in the search tree in order to come up with a guess about where the best moves are going to be, and they use that to sort of narrow their search. So they're not reconstructing the whole tree. It's not a brute force search. It's a Monte Carlo search. It's a statistical search. It's a random statistical search. I have actually diagrams of Monte Carlo search later on, but just on. Let me actually see where that diagram is. No, it's in the next. It's in the next. Yeah, in the next lecture, I will be talking more about neural networks and how artificial neural networks work. AlphaGo is a neural network. It uses neural networks to train the searching, the look ahead. And we'll go into a little bit more technical detail about how these neural networks work. The point for our purposes is just that these neural networks are fast enough, strong enough to beat our top-ranked Go players. So AlphaGo beats Kijia in 2017, but that wasn't the first top-ranked Go player that AlphaGo beat. The earlier, where are we? Yeah, the earlier game here. The earlier game is here. So one of the challenges with playing against Kijia is that Kijia and the other top-ranked Go players are Chinese, and it's politically a difficult thing to have an American tech company sort of slaughter on the Go board a Japanese top-ranked Go player. It's sort of, there's a political impropriety there to just jump out and do that. So to build up to that point, AlphaGo had been playing other top-ranked players, and maybe the most famous of these matches was Lee Sedol. So Lee Sedol is the 6th highest-ranked Go player. So he's no slouch. He's a very highly ranked Go player. Not the top, but the 6th rank. But he's also from South Korea. South Korea has a very strong Go playing culture, and Lee Sedol is a very good player. But South Korea is friendly with the United States, friendly with U.S. tech companies. So it wasn't that big of a deal to get Lee Sedol to play against AlphaGo's, Google's computer. And so I believe this was in 2016 2016. Lee Sedol plays AlphaGo. This is the match. I kind of want to just play this one clip because I think it demonstrates well how humans playing computers at these games goes. It's basically the same dynamic that we saw with Kasparov in Deep Blue, where Kasparov, in some sense, underestimates what the machine's going to do, and then when the machine does something that it doesn't expect, the humans get blown away. So you'll see that happen here. This is move 37. So AlphaGo played Lee Sedol 5 times, 5 games. Lee Sedol only won 1 game. AlphaGo beat the other 4 games. Before this tournament, no one had really seen a computer Go playing system that could beat top-ranked players. And when Google announced that it was going to have this match, everyone was sort of skeptical that AlphaGo was going to do anything. But then AlphaGo goes on to beat Lee Sedol 4 times. And this is one of those matches where AlphaGo wins. This is match 2, and this is the famous move 37. There's lots of commentary about this particular move. So this is the game. This is the actual board here in the corner. This is the time. Each player gets 2 hours or so to make their moves, and the computer's printing out to the screen what moves to make. And then there's a human player down here who's putting stones on the board to match what the computer tells. And then the main screen here are the commentary. This was on Twitch. Commentary on YouTube also. Commentators talking about the game as it's being played, what the good moves are. And you'll see at the beginning of this clip, the commentator here is talking about how it doesn't make any sense for black to play moves in this area. He says, look, white has a very strong position in this corner with these white pieces, and so it really doesn't make any sense for black to play here. Black should be playing somewhere else because this is a pretty strong white territory. So this is what the commentator is going to start, and not surprisingly, AlphaGo is going to play exactly here, and you'll see the human response.
And so the value here is relatively small because it doesn't spread out, and also because these stones, if black chose to play a lot of moves on the right side, he would not have the added value of having, say, an attack on this group because it's so strong. And so that's something you look for. And it changes the value of an area when you have a strong group like this, because black doesn't have any point to approach it because it's so strong.
And this is what Thore from the Google team was talking about. Is this kind of evaluation value?
That's a very surprising move.
I thought it was a mistake.
Well, I thought it was a quick miss, but
a clicko. And if we were online Go, we call it a clicko.
Yeah, it's a very strange. Something like this would be a more normal move.
Okay, actually, you're going to have to. So Do you have to think about
this? This would be a
this?
kind of a normal move, and white would
Sure.
answer here. But actually, since this group is so strong, maybe white wouldn't.
Okay. Oh, right. That's right. Because what you were just saying, that's just settled. Right.
Because even if black does stuff like that, even after playing all its moves, it's still strong.
It doesn't change it, right?
Doesn't change. Well, these stones might get a little weak, but the value of this is relatively small. So we don't really know if white would answer this or not. White's going to answer this. This is almost as close as an attachment move. It's diagonal, so it's a bit further away, but like if black continues with this, it would be very effective.
Interesting. So AlphaGo played this move, which I want to hear more about in a second, but Lee has left the room.
He left the room after that.
He left the room after that move.
Uh-huh.
I mean, I'm not even going to ask. I mean,
he had to go and wash his face or something just to recover from it. It's a very surprising move.
It's a surprising move.
I wasn't expecting that. I don't really know if it's a good or bad move at this point. Usually white would be just happy to play here. Black probably is thinking of doing either this or maybe something like this to sort of make a... So the direction of play is not so unreasonable.
Okay.
And that black is sort of expanding this network here. And
Yay. Yeah, so...
So
after talking about how it doesn't make any sense to play in here, AlphaGo plays exactly there, and it shocks everyone to the point that the opponent, Sedol, has to get up and go to the bathroom. Like he is so shocked by the move that it pushes him out of his seat. Very similar, I think, to the story of Garry Kasparov being shocked by this queen sacrifice move. Not the kind of move that you would expect. And you can see the shock in their faces as they're talking about it here at the beginning. The guy sitting here talking about how it doesn't make any sense to play this move. AlphaGo plays this move, and then he looks... I mean, he does a quintuple take. So 1, 2, 3. He looks at the board. He still doubts it. 4... And he looks back one more time, 5 times. It was a 5 take. That it shocked him so much that he had to look back and double check 5 times. And at the beginning, he's saying it doesn't make any sense to play this move. At first, they think it's a mistake. But by the end of this video, in just a couple minutes, they convince themselves that, in fact, actually, this is not such an unreasonable move. It's actually a rather shocking move. And it puts AlphaGo in a position to eventually win this game. So it looks like a miss, it looks like a mistake, but it's actually the right move. It's actually the move that gets AlphaGo the win. Uh-oh. Oh, I guess it took off the thing. Sorry about that. There we go. No, that's not what I want. I want this. All right, sorry about that. Yeah, so AlphaGo pushes Sedol out of his seat, and the players underestimate AlphaGo the whole time. They don't expect that the machine can make these kinds of moves, and AlphaGo ends up winning this match and winning 4 of these 5 matches. In fact, it's incredibly impressive that Sedol was able to take any games at all. Sedol takes the 4th game off of AlphaGo. 4th game? No, the 5th game. I'm sorry, the 5th game. Let me double check that. Yeah, this is move 78 of game number 5, and it's sometimes called the Hand of God. This is Lee Sedol making this move. I just want to give a brief discussion of what Lee Sedol does in this move, in this game. So here's the board. This is Lee Sedol versus Alphago. Final match. Lee Sedol has not won any games yet, and Alphago is in the lead. And Lee Sedol spends about half an hour, 40 minutes or so, on just this one move. So the way it works, Lee Sedol only has 6 minutes left. Alphago has over an hour left. And once Lee Sedol runs out of time, he has to make the next move within 30 seconds, I believe, and he doesn't get any extra time to think. So when the clock runs out, it doesn't mean the game's over, but it means that he doesn't have any extra time to think. So Lee Sedol spent all of his thinking time on this one move, this Hand of God move, move 78. And in fact, he had been up the night before with his colleagues all night. He barely got any sleep before this match because they had been trying to figure out a way of breaking Alphago, of getting Alphago out of its routine where it's just dominating the board. And here's where Lee Sedol does it, and I'll even tell you the moves that Lee Sedol ends up playing. So here's the board, and for move 78, Lee Sedol puts his white stone right here, and that looks like a weird move, maybe. If you're not a Go player and you just know a little bit about the rules like I do, it looks like a weird move. For one thing, there's not a lot of white pieces around. All the white pieces are blocked by other black pieces. For another thing, you're putting your white piece right between two black pieces. That takes away two of its liberties. It's almost ready to get captured. There's another black piece down here so there's not a lot of room for this piece to grow. It looks like a bad move. But in fact, it's exactly the right move. It's the right move in the sense that it throws Alphago off its game. Alphago was not expecting this move. It's not the kind of move that's the kind of move that anyone would expect. And this is why Lee Sedol had to think about it so hard. Right? Lee Sedol's goal here was not just to play the best Go move, but was to play a Go move that got Alphago off of its game. And playing this move that doesn't look like a good move at all is exactly what did it. After Lee Sedol plays this move, I'll go ahead and show Lee Sedol actually playing it. After Lee Sedol plays this move, Alphago starts making all sorts of weird moves, playing in random corners, and just sort of the moves that Alphago is making just don't seem to make any sense. And it's really because Lee Sedol was able to find this one move that, there it is, that throws the game open. It took him a half an hour sitting at that Go board and the whole night before working with his colleagues to actually find this move. Really only an anime reaction is appropriate for the level of intensity here. But just the fact that he could find this move at all, that he could find a move that would get Alphago off its game, it's incredibly impressive because this is the last time this will ever happen. This is the last meaningful match that a human will ever win against a computer. Now the computers are too smart, too fast, and humans don't have a chance against them. But this one last move, this one heroic last move from Lee Sedol, by the time Alphago gets to Kijia, it's already much more powerful. DeepMind had upgraded Alphago several times to get ready for Kijia. After Alphago beat Kijia in China, DeepMind wanted another challenge, and so they decided to make Alphago Zero. And the challenge with Alphago Zero is that Alphago Zero would not have any training matches to draw from. So for the original Alphago, it uses Monte Carlo tree search to search the algorithm, to search the search space effectively, but it trained the neural network on lots and lots of games, historical games, millions of games that have been played in tournaments, that have been played between other computers, and it used those other games in order to train itself. So the computers needed a big backlog of games. You needed to see lots and lots and lots of games in order to play good chess. With AlphaGo Zero, DeepMind built a machine that didn't need to look at any other games. So there was no training from other games that went into AlphaGo Zero. Instead, AlphaGo Zero learns only by playing itself. So when it starts, it plays itself and it does really badly. But it learns from that self-play to improve slowly over time until eventually it passes the AlphaGo that beat Lee Sedol. It then eventually passes the AlphaGo that beat Kijia in China, and then quickly becomes the fastest, the best Go playing computer in the world. Alphago Zero, goes from never having seen a Go game at all to 21 days later being the best Go player on the planet. And this isn't just about Go. Just a few months after that, they used the same basic framework, sort of Monte Carlo tree search with the neural network selections. They used this to build a general game-playing computer they call Alpha Zero. And they trained Alpha Zero to play against itself on chess, on Go, and on Shogi. Shogi is another board game similar to chess and Go. And after a number of steps, Alpha Zero quickly became the best chess player in the world, the best Go player in the world, beating even Alphago Zero, and the best Shogi player in the world. Now, this ranking is a little bit disputed. Alpha Zero played a version of Stockfish that's not the best version of Stockfish. And so after Alpha Zero published these results saying, look, it can beat Stockfish, even our neural network can beat Stockfish, Stockfish came back and said, oh yeah, well, let's prove it. And there have been, over the last couple of years, a series of really high-profile matches between Stockfish on the one hand, and not Alpha Zero, but Leela. So Leela is a open-source model based on the AlphaGo framework. So this is our best neural network versus our best classical computer playing chess. These chess games are ruthless. If you know anything at all about chess, these chess games are stunning. The players sacrifice pieces like they're nothing. They take really risky moves that you think no human would play. It's pretty clear, if you know anything about chess, that these are not human beings playing these chess games. These are not the kind of chess games that human beings would play. So it's really fascinating to watch these computers play each other. But what's maybe more important for the rest of the AI world is just the fact that you can build a general-purpose computer that plays not just one game well, but plays a whole host of games, each of them different and difficult in their own way, but you can have the same system that can learn to play all of these different games. And they're genuinely learning. So if I get rid of this, when I say genuinely learning, I mean that they are coming up with strategies that weren't programmed in originally. So there's lots of examples of this in chess and Go, but I think maybe the easiest way of seeing an example of this is with Breakout. So Breakout is this game that we've all probably played where you have a little paddle and a ball, and you're supposed to hit the ball up to knock out these bricks. And the more bricks that you knock out, the higher your score. And if you can knock out several bricks in the same bounce, then that's really great for the score. So this is a neural network from DeepMind learning to play Breakout. And what it learns, first of all, is how moving the paddle in various ways gets it to hit the ball back and it gets it to raise the score. What it's trying to do is just optimize the score, just get the best score it can. And it plays different ways, it tries out different strategies, and some of them work and some of them don't. And you can see by a few hundred iterations, it's getting pretty good at Breakout. But after 240 minutes, after running it long enough, it discovers the big trick to Breakout. The big trick, I'm sure you all know, is that if you can get the ball to open up one of these side channels to get into the back, then the ball will bounce around the back and it'll just keep hitting other bricks, and your score will go through the roof. And this program found that strategy. So the programmers didn't have to program that strategy in. All the programmers did was say, okay, do what you can to try to optimize your score. And the computer tries a bunch of different things and eventually finds a strategy that's super successful. Any human being that you give Breakout will eventually find the strategy, and they'll realize that this is the right way of playing. And this system can do the same thing. In fact, it can do this with any game you give it. The DeepQ system can learn to play any Atari game and do well very quickly, perform much better than you can at that same Atari game. Let's come back here. DeepMind has recently put that same method into StarCraft. StarCraft is a real-time strategy game. It's very hard. Some people talk about it as the chess of gaming. One of the reasons why it's like chess is because it's a two-player game. You have a definite start state, and winning conditions. But it's real time, so it requires not just strategic moves, but it also requires playing fast, being able to control all your units. Sometimes you can have something like 200 different units on screen, and the players have individual control over all these units. There's also, in StarCraft, there's an early game and a mid game and a late game, just like in chess, and some of the strategies are modeled on chess strategies. So for all these reasons, StarCraft has been a target of artificial intelligence research for a long time, since the 2000s. There have been StarCraft AI research, people trying to build AI that can play good StarCraft. No one's ever been able to do it very well, but after AlphaGo got all these big wins against chess and Go, and they needed something else to conquer, StarCraft was the next one on the table. As far as I know, DeepMind still has StarCraft AI bots on the ladder, playing against real human players, and that it has reached Grandmaster level on the ladder. As far as I know, no AI has actually played in tournaments against humans in ways that, like the tournaments against Kasparov or Sedol or anything. So we're not yet at the stage where AI is definitely better than humans at StarCraft. AI can beat most humans at StarCraft, but maybe not the top level players. We haven't really seen that tournament yet. I wrote a little essay on what would count as a fair game of StarCraft, given the fact that the computer can control all the units. How do we know that the game is actually fair? In particular, the first demonstrations of AlphaStar playing StarCraft showed that the computer was actually seeing the entire map at the same time, and human beings can't do that. Human beings have to move the map around to various locations. So in some ways, the computer was cheating. AlphaStar, in the time sense, it doesn't do this anymore. It's only looking at limited versions of the map. But there's a question, because you can get the computer to move as fast as possible, and that's usually a lot faster than human beings. There's a question of what counts as a fair game in StarCraft. So I have a little bit of thoughts on that in this essay, if you're interested in that. We're almost done here. A couple of years ago, some researchers sent out a survey to other AI researchers asking when will computers beat humans at various tasks. And these are the results of that survey. You can see how this stuff is really precarious with respect to time, because when they sent the survey out, by the time they got the survey back and published it, some of these had already been beaten. So Angry Birds was not beaten when they sent out the survey, but by the time the article was published, computers had beaten the world champions at Angry Birds. Computers had learned to play Angry Birds and learned to play them better than humans. Same thing with the World Series of Poker. There are now computer poker player, Texas Hold'em players that are better than a human, that will win the pot over you. And this has been demonstrated in tournament-style demonstrations. Exhibition matches. So the rest of these are different tasks and how long in the future it'll be until we get a computer to solve it. So getting more and more into the future, and this is like far deep future. So Angry Birds, World Series of Poker, if you can't read on the screen, the next one up here is folding laundry. Folding laundry is actually something that's rather difficult to get machines to do. Working with soft materials in general. Machines are good with hard materials that can you can grab and move around, but folding laundry requires a lot of sort of delicate finger work, and it's not the kind of thing that we have machines that are very good at. And StarCraft is the next one on this list. AI researchers have known for a long time that StarCraft was a tempting, low-hanging fruit that was sort of just around the corner. So when DeepMind announced that AlphaStar was going to play top-level StarCraft, people were expecting it. It wasn't very surprising that it was happening. Transcribe human speech, translate speech, being a telephone operator, assembling Lego systems, assembling IKEA systems, playing all Atari games. We actually have computers that can play most Atari games. I think there's still some that aren't there. You'll notice here that it says in the future playing Go with the same training as a human. So we already saw that Go playing computers can beat top-ranked Go player humans, but they require many more training samples. Even for Alpha Zero that wasn't using other Go games, it still had to play against itself millions of times. So these computers are drawing from millions of games, experiences of millions of games, in order to train to perform at the level of a top-ranked Go player. But most human players who reach that level don't encounter millions of games. Computers can do it in a couple of seconds, whereas humans, it takes time to go through a Go game. You can only go through so many Go games in your life. So most human players, it's estimated that most human players who reach a 9-dan level or similar for chess players who reach a grandmaster level, have played something like 50,000 games, which is a lot of games, but it's much, much less than the million games required to train these computers. So you can get computers to play Go at the same level as humans, but not with the same training set. So one benchmark that's still out in the future is, can you build a Go computer that can play, that can meet humans with the same training data, the same size of the training data? There's other goals here, things like robot races and stuff. In the far, far future, there are things like write a New York Times bestseller, write a top 40 pop song. Math researcher, surgeon, AI researcher is way out in the future, full automation of all human jobs. Most AI researchers are not expecting full automation of all human jobs anywhere in the near term. That's somewhere in the long or very long term. These are error bars on the sides of the Okay, so you see some of the predictions about what's coming. You see that we're not expecting a whole lot from AI even in the next 15 years. We're still anticipating things like able to play Go, able to work as a retail salesperson. This is the anticipation that AI researchers have about the near future of AI. None of this is take over the world or anything like that. One thing that's not on this list, but is probably worth mentioning in terms of human-machine competition, is RoboCup. RoboCup is a yearly competition of robots playing soccer. There's actually several different size categories. There's tabletop ones that are about the size of a pack of cigarettes or deck of cards. And then there are these sort of knee-high ones that are bipedal. They're walking on two legs. Notice that the robots here are standardized, so they're all using the same model of robot, and what's different between the two teams is the program. So they're programming it different ways. So they're responding slightly different to the ball, to the other players around them. They have cameras on them. They can walk around, not very well. And the goal is just to play soccer, is to score more goals than the other team. They're not very good, but the RoboCup goal is to have full human versus robot soccer game by 2050, say, 2040. Right. The idea is that you can demonstrate not just how intelligent these machines are, but also how good they are at cooperation, and just how good they are at navigating our world by playing soccer. Soccer requires physical endurance, it requires strategic thought, it requires cooperation, communication between members of the team. Obviously, you can build machines that are stronger than humans, but can you build machines that have the endurance of a soccer player? This is something that we're not anywhere close to yet. Human professional soccer players can easily beat our best machines, but maybe that changes in the future. I think it'll be really hard to deny that computers or robots are intelligent when they're doing something like beating us at soccer. It's such I think the example is more accessible than chess. Is something that we're all familiar with. It's something that we're all familiar with in terms of what it takes to play both on an endurance level and on a strategic thought level. And seeing machines beat our best professional players, it'll be a very impressive event. It'll be a watershed event, I think. So something to look forward to in the future, these human-machine competitions. There might be a question you're having, like, are these machines really playing this competition? Like, does the machine really care that it wins or not? Are we really proving anything about what the machine can do? Or maybe we're just proving something about what the humans can do? Maybe Deep Blue didn't really beat Kasparov. Maybe the engineers who built Deep Blue beat Kasparov. And that Deep Blue doesn't deserve any credit on its own. This basic idea is associated with Lovelace's objection. Lovelace's objection is basically that computers only do what we tell them to do, or that the analytical engine can do whatever we know how to order it to perform. It can do what we tell it to do. So Lovelace's idea is that maybe the machine doesn't get credit, maybe we get credit, and the machine doesn't get any credit at all. If Lovelace is right, then maybe the machines aren't really being intelligent either. Maybe Deep Blue's intelligence is all just a facade, and that the real intelligence is in the engineers who built Deep Blue, and not Deep Blue itself. Maybe, or maybe not. This is where I'm going to end the discussion. We will come back next time and talk more about artificial intelligence in terms of whether machines can think, whether robots deserve credit for what they do. This is all coming down the pipe. But I've talked long enough. This is almost 2 hours long. I'm sorry for the long video. I'll see you next time in Lecture 3. Bye.